the component in the not seismically upgraded configuration, so it will be the orange line in here. While the second loss dp function is the component in its seismically upgraded configuration, which is the blue line in here. Now, the difference between something about how much would be the impact of a non-structural upgrade in terms of seismic loss reduction. So we define a parameter, which is this delta L max that you see in here, so this maximum loss reduction, that tell us which is the maximum loss reduction that we can expect from the upgrade of that component in the ADP range of interest. And the way the filtering is performing in the first step is by assuming a threshold for these maximum loss reduction parameters, and by comparing for each non-structural upgrade the value of estimated maximum loss reduction with the threshold that we assume. Now, if the maximum loss reduction is below the threshold, the component is removed from consideration. If it's above the threshold, then the non-structural upgrade is further investigated in step 2. Now, in step 2, again, very simple, so we are going to perform the filtering, and this time the parameter that we are going to use is the ratio between the maximum loss reduction calculated in step 1 and the upgrade cost. So this parameter tells us something about how much that is cost to upgrade a component compared to this maximum potential benefit. So again, we assume a threshold, we compare the value that you obtain with the threshold, and only components above the threshold we go to step 3. Step 3 is very simple, so the only difference in step 3 is that we are changing now the ADP range of interest. So this time, this ADP range is based on some structural analysis, and so we assume maximum drift and acceleration based on the response of our structures. Again, we calculate again these parameters, we compare with the thresholds, and only components which are above the threshold, we go to step 4. So finally, in step 4, we estimate the expected and loss variation due to each non-structural upgrade. And we can do that by using the Ramirez-Miranda approach and the loss EDP function that we have calculated for each component. Then we input this expected and loss variation in the benefit-cost ratio equation, and we obtain for each upgrade a benefit-cost ratio, which is the parameter that we are going to use to perform the prioritization. Now, I will show you a case study building application that I'm sure will clarify how the framework works. So we use 3 steel momentary steam frames that are taken from the Sac Steel project in California, and that are characterized by brittle welding beam column joints. And they have 6, 3, and 9-story building. Now, first we developed the loss ADP function of our elements using fragility and consequence function from the FEMA P58 database. And then we start to apply the 4 steps of the framework. So for the first step, again, we don't need really any structural analysis. We're just considering the occupancy of the building is office buildings. And we are assuming a very large ADP range, just 5% as maximum drift and 5G as maximum peak flow acceleration. These are not likely to be achieved by the building, but we just wanted to assume a very large ADP range for illustration purpose. And also, we are assuming a maximum loss reduction threshold, which is equal to 0.1% of the building cost. So the threshold is the blue line that you see in this graph. The black dots are the components above the threshold. The red one are the components below the threshold. Now, if we look, for example, at sprinkler piping, which are below the threshold, what you can see is that the 2 loss ADP functions that we have estimated for this component are very close, which means that independently from the structural response, so independently from the actual peak flow acceleration value that we would have in the building, the maximum potential loss reduction that we can have due to the upgrade of this component would be 0.08%, which is below our. Now, if we look now, for example, at the we can see that the maximum loss reduction is now 58%. So still, we cannot say of the upgrade because we don't know yet which are going to be the actual peak flow acceleration. However, we can say that this component may potentially have a significant contribution to seismic loss reduction. So now, moving to step 2. In step 2, we are also using the upgrade costs that are taken from the literature, and we are assuming a threshold for the ratio between the maximum loss reduction and the upgrade cost. Again, the ratio is just the blue line, And for example, if we look at one red dots, which are curtain wall glazing, what happened is that curtain walls were having a large maximum loss reduction in step 1. However, the upgrade cost of curtain glazing is so high compared to the potential maximum benefit that this component is considered to be not viable as upgrade. And this is because we assume that the upgrade cost of curtain glazing involves replacing the glazing, which is very expensive. So what this result is telling us is that this upgrade has an upgrade cost which is too high compared to its maximum potential benefit. Now, moving to step 3, in here we are just modifying the ADP range, and we assume our maximum engineered demand parameters, the one that we obtain by running time history analysis at the maximum credible earthquake level. And what you can see is that for some component, since we are changing the ADP range, we are modifying these parameters and we are reducing these parameters, which are now lower, for example, for suspending ceilings, that what we to. So finally, moving to step 4. In step 4, we are running time history analysis. We are calculating the expected non-loss reduction associated with each upgrade, and we are estimating the benefit-cost ratio. So we assume 40 years for occupancy time and 4% for the internal rate of return. Now, if you look at these results, you can see that for all buildings, the order or the first upgrades is the same. So basically, we have first chiller with the highest benefit-cost ratio, followed by cooling tower and low-voltage switchgears. And only for the 6- and 9-story building, we have that the upgrade of chiller has a benefit-cost ratio larger than 1. So we have obtained our results. We are prioritizing our non-structural elements, and we found out which one worth the investment. Now we need to validate the results. And the way we validate our results was by using the FEMA P50A methodology. So basically, we implement our performance model in PACT, and we estimated using PACT, that is the tool that implements the FEMA P50A methodology, we have estimated the expected non-loss reduction corresponding to the upgrade of each component. And with this expected non-loss variation, we recalculated the benefit-cost ratio, which are now the red X that you see in this graph, that are compared with the black dots that are the value of benefit-cost ratio that we have estimated using our framework, so the loss ADP functions that we have developed. So as you can see, the framework is able to capture which are the most important components that are able to optimize the benefit of the investment. There are some discrepancy for some components. The largest one are the one for chillers. And this is expected because in the simplified framework, we are neglecting some source of uncertainty, which are the uncertainty in the structural response and in the repair cost. So because of this neglection, of course, we have some discrepancy within the full probabilistic approach of the FEMA P58 and our framework. But overall, it seems to be able to capture the main important component to be upgraded. Now, just to conclude this part of the presentation, we have developed an Excel tool that can be downloaded. This is the QR code to do that. And this tool can be used to run each step of the framework. So depending on the intent and the resources of the designer, they can decide to run just the first preliminary steps or all the steps till the final prioritization. So now, moving to the second framework. The second framework was developed to assess integrated structural and non-structural upgrade strategies. So the first things that we need to do to apply this framework is to define our performance objective. So which performance objective do we want to achieve by upgrading the building? And these performance objectives are defined in terms of probability of collapse and expected non-loss. Then we need to define the structural design alternatives that we are going to investigate. So after we define this initial input, the first step is the hazard analysis. Then we can run for each structural design alternative the structural analysis. We can already perform the first check on the probability of collapse. So if the probability of collapse not satisfies the performance objective, then we have to modify our structural design. On the other end, if it satisfies the performance objective, we can move to the third step, which is the loss estimation step, and we can apply our framework to identify which non-structural elements needs to be upgraded in order to achieve the expected non-loss performance objective. Now, if even by upgrading all non-structural elements inside a building, we are not able to achieve the expected non-loss performance objective, then again, the structural design needs to be modified. On the other hand, if we are able to achieve it, then we have obtained our output, which is a viable integrated structural and non-structural upgrade strategies. Now, just for the structural response, we used the just simplified approach that have been proposed in literature. So for the drift estimation, we are using the capacity spectrum approach, while for the acceleration, residual drift, and collapse fragility, we are using simplified equation and approaches that are provided in the FEMA P58 guidelines. Then for the loss estimation, again, we're just using the Ramirez and Miranda approach with the loss ADP functions that we have developed. And so let's go directly to the framework application. So for the probability of collapse, we assume a performance objective of 20% probability of collapse at maximum credible earthquake, while for the expected non-loss performance objective, we assume 0.2% of the building cost. We assess 3 structural design alternatives. Now, the original building is the 6-story moment-resisting frame that we have already discussed when we applied the first framework, and we are retrofitting this building using hysteretic dampers and viscous dampers. Now, first, we assess the performance of the original building, so this is the pushover curve that we obtain, and we obtain a very large value of probability of collapse at maximum credible earthquake equal to 62%, which was definitely above the performance objective. So we perform a preliminary design of the hysteretic dampers, and just with the preliminary design, we reduce this probability to 44%, but still too high compared to the performance objective. So we iterate on the properties and the location of the hysteretic dampers till getting a probability of collapse of 22.4%. So this probability of collapse is still above our performance objective, that was 20%. However, for illustration purpose, we consider this probability close enough to the performance objective, and we are going to perform the loss estimation step for this structural configuration. For the viscous damping retrofitting option, same thing. So first we assume a viscous damping ratio equal to 20%. The probability of collapse was still very high, so we increased the damping to 35%. We're close to the performance objective, but we did not reach it yet. However, you will see we will apply the loss estimation step also to this building configuration. So moving to the loss estimation step, we calculate first the expected non-loss for the building with hysteretic dampers. And we found an expected non-loss equal to 0.28%. So this expected non-loss was too high compared to the performance objective, that was 0.2%. So we apply our frameworks, and we obtain that chiller and air handling unit were the critical non-structural elements upgrade to be implementing in order to achieve the expected non-loss performance objective. And these results make sense. When we are retrofitting the building with hysteretic damper, we are increasing the stiffness of the structures, and therefore we are increasing the seismic demand on the acceleration-sensitive non-structural element inside the building. So what this result is telling us is that in order to obtain a viable upgrade strategy, we have to combine the upgrade retrofit solution with hysteretic dampers with the upgrade of 2 acceleration-sensitive non-structural elements. Now, for the building with viscous dampers, on the other end, we are able to achieve our expected non-loss performance objective without the need to implement any non-structural upgrade. So basically, this is telling us that for this case, viscous dampers are more effective in terms of seismic loss reduction compared to hysteretic dampers. So we have obtained our output that are 2 viable integrated structural and non-structural upgrade strategies. And now, to validate the results, again, we use the FEMA P58 methodology. So we implemented, in fact, our model of the original building, of the building with hysteretic dampers, of the building with hysteretic dampers and air handling units and the chillers upgraded, and with the building with viscous dampers. So as you can see, we have some differences between the framework and the FEMA P58. However, the framework is able to capture which combination of structural and non-structural upgrade are below the expected non-loss performance objective. Now, moving to the conclusions, we have proposed 2 frameworks, and we found that these were able to provide insight into non-structural upgrade impact on seismic loss reduction, and they were able to identify viable combination of structural and non-structural upgrades. We found a substantial loss reduction of the computational time when applying the two proposed framework compared to the full FEMA P58 methodology, and we developed an Excel tool to facilitate the practical implementation of the non-structural upgrade assessment framework. We found that the use of component velocity P functions which directly relate engineered demand parameters with expected losses improved the transparency of the non-structural upgrade assessment process, as it helped understand how much can be the impact of a non-structural upgrade and how much it can be sensitive to change in the structural response. And finally, we found that the use of 4-step, which requires different level of sophistication of the input data, is very practical and efficient to obtain relevant information on non-structural elements upgrades impact without necessarily investing a large number of resources. Thank you.
Thank you, Alessandra, for the presentation, which allowed us to recover at least 2 or 3 minutes. Now, let's open the floor for the questions of the evaluation committee. Flavia. I think the microphone is turned off now.
It's me. Okay, so one question. You have shown, the first framework you have shown was applied to the case of a 3-archetype steel structural building. My first question is, do you need any change to the current, so if I was downloading the Excel spreadsheet, is currently the Excel spreadsheet ready to be used for other structural typologies? Is a methodology independent of the structural typology, or would you need to tweak anything?
Thank you for this question. So actually the frameworks can be applied to other buildings, so it's not related to the building we are using, because I will just go to this part of the presentation. Basically how the framework works, you have to input the different input data required for each step. So for example, as you see, the first input are very general, so they do not depend on your structures. Then also the upgrade cost, depending on which non-structural elements are you considering. So if they change, you may want to change the upgrade cost as well. And also, let's say, about the structural response, this really is something that will be done by users of the framework. So it is applicable also to other building typology.
As it is, so it doesn't need any tweak. And in terms of categories of non-structural damage, do you think there is any site-specific, country-specific aspect that would need to be considered in tweaking this methodology for different regional area, for different regions?
Yes, I mean the selection of the type of non-structural elements, the vulnerability of the non-structural elements may depend on the country where you are applying the methodology. So that is something that users of the framework should decide when they use the framework. But right now, it has, for example, the tool has access to the FEMA P58 methodology, a database. So if you want to select like other fragility or consequence function for the methodology, you can do it. But if you want to assume more specific fragility functions based on other considerations, you will need to modify the parameters of the fragility in order to apply.
One last point, in terms of this modification, the current tool, can modify it, or closed tool? So how open is the tool?
Okay. Right now it can, let's say, the database that it's a separate part that is not intended to be modified by the user, but it's simple things to modify. So future works can also extend these. Or,
Thank you.
Yeah.
Thank you.
Thank you.
I can have just a quick question, but I think you already answered it while answering to Flavia, because I was going to ask, so the database of component EDP2 loss curves, where does it come from? Because you show basically the framework, but you never say exactly where the data that you used comes from.
Yes. Okay, so basically we take just the fragility and consequence function from the female P58, and we are upgrading some of them based on more recent research work, the one published by Steneker in 2022. So some of the fragility have been modified to account for some updates, but the basic database is the one of the female P58.
Thank you.
Thank you.
Thank you for quite interesting presentation, and I agree completely that a lot of work has been done. So I have a very simple question about did you take into consideration the age of the building that you are considering in your framework? And I will get directly to the point, because I saw in the table a lot of non-structural elements and quite different of them. Some of them are machine, equipment, some of them are wall partition and everything. So that's why I'm asking, is the age as a factor taken into consideration?
The quantities of the non-structural elements depends on also this. So we are considering, let's say, the type of non-structural elements are the same for all the buildings, but the quantities of them will change based on the buildings.
I'm asking you this because for type of equipment and everything, we have so-called depreciation period. So if, for example, chiller, and if the age of the building is 20 years, so definitely I should replace chiller without any earthquake effects on seismic effects. So that was my point. Okay. Thanks for the question, for answer. Thank you.
Thank you. We are back on time, so I can open the floor for one question of the audience, if someone else from the audience wants to ask anything. If not, then we will just thank Alessandra again.
Thank you.
And move on to the third candidate of this first session of the afternoon, Almouyed Bella Nafeh from Lebanon. He will be talking about loss-based methodologies for large-scale assessment of non-ductile infield reinforced concrete buildings.
Thank you very much, Professor
Go ahead.
Montero. Thank you very much, Professor Montero, for the introduction. And good afternoon, everyone. And thank you all for taking the time to attend today's presentations. I couldn't have picked a better audience to share this career milestone with here today. My name is Almouyed Bella Nafeh, and for the past 4 years, I've been working on advancing risk and loss-based methodologies for the building-specific and regional assessment of non-ductile infilled RC frame structures. This work has been done in collaboration with my supervisor, Gerard O'Reilly, whom I hold in the highest regards for his continuous dedication and, most importantly, friendship. So without any further ado, what seems to be the issue here and how can we address it? Well, if we were to inspect our regional building stock, we would discover that infilled RC buildings occupy a significant portion of the existing built environment, and that the majority of said buildings were designed before the introduction of modern seismic provisions. For example, buildings constructed before the 1970s were designed to resist gravity loads only, and it wasn't until the beginning of the 1970s that we started witnessing the implementation of the equivalent lateral force method as a substandard mean to quantify the seismic action a building is expected to resist. To add more insult to the injury, URM panels were considered as non-structural elements, and they were discarded from the initial design process, neglecting their effect on the surrounding frame elements and causing detrimental consequences, as post-earthquake observations have shown. And whether we're talking deaths, dollars, or downtime, governments grew aware of the gravity of these consequences and urged policymakers to draft incentives to incentivize building owners to carry out retrofitting actions. In Italy, this is the so-called sisma bonus. It's an incentive that allows you to deduct the expenses incurred to carry out seismic reduction work, improving the seismic class of the property that is the subject to the intervention. But where does our contribution lie? Well, we propose a relatively fast and reliable method for the building-specific loss estimation of non-ductile infilled RC frame buildings a procedure that could define the technical standards behind Sisma bonus for this typology of buildings. The proposed methodology allows practitioners to deal with the sophisticated concepts behind modern probabilistic seismic assessment in a simplistic manner. And the procedure integrates open access tools and models for the characterization of seismic hazard, strength deformation relationships and robust approximations to quantify the seismic vulnerability and the seismic demands, and high-fidelity mathematical models and state-of-the-art methods for the estimation of seismic risk and losses. But first, assessing the seismic performance or validating code-based procedures requires analyses performed on building models that are considered widely representative of the building class under investigation. These models are generally referred to as archetypes, and so as a first effort, we dealt with the development of a database that includes archetypes of infilled RC numerical models. First, to fully incorporate the most prominent features of a regional design space, an identification of the geographic construction practice and conditions is necessary, and this was accounted for following an in-depth review of past guidelines and design approaches. Now, this database incorporates two design approaches, namely GLDs, or gravity load design buildings, and SSDs, or substandard design buildings, using the equivalent lateral force method. Second, the geometric configuration and architectural features of the database should be significantly representative of both time and space. This was addressed based on expert architectural judgment following numerous consultations with practitioners and architects. Now, this effort resulted in 7 different architectural layouts and 105 numerical models in total. The models were OpenSeas using a 3-dimensional lump plasticity approach and considering the latest state-of-the-art numerical models which were calibrated on experimental basis. We made this database accessible and available for download on GitHub for all the scientific community to take advantage of. But most importantly, the database is user customizable, meaning that your input variables are stored separately, which enables the users to tweak the models based on their own design and detailing assumptions. The repository also contains sets of hazard-consistent ground motion records, conditioned on different intensity measure types, and master files for running all sorts of analysis, from a basic static pushover analysis to a much more complex multiple stripe analysis. But perhaps the biggest testament to the robustness of these numerical methods was the outcome of the blind prediction contest organized by ISAC, an Italian startup based in Milan that is involved with the design and production of active mass dampers. And ISAC tested a large-scale specimen corresponding to a 3-story infilled RC building in its as-built condition here at the U-Center facilities in Pavia. We then idealized the full-scale model into an OpenSeas, a full-scale specimen into an OpenSeas model, which according to the unveiled results performed generally well, earning us first place in the contest, but most importantly, the satisfaction of validating these numerical tools early on. And now that we've got the validation case studies out of the way, we've devoted most of our efforts to drafting a comprehensive building-specific procedure termed PB loss for pushover-based loss for the seismic risk classification and loss estimation of existing infilled RC buildings. This procedure went through many iterations, refinements, and multiple validations along the way until I could finally stand in front of you here today and present it. And it looks like this, starting from the hazard component. The user is first required to calculate the mean hazard curves associated with PGA, a conventional IM that is typically used for its simple definition, and average SA, the protagonist in all recent studies on efficiency and sufficiency of intensity measures. This can be carried out using open access tools and models such as the OpenQuake engine or the European Seismic Hazard Model of 2020, for example. Then the user must identify the intensity levels corresponding to mainly 4 code-based return periods, and in this approach we refer to the NTC 2018 limit states, which is named operational, damage limitation, life safety, and collapse prevention. Finally, a second order fitting to the average SA hazard curve is carried out for purposes we will highlight later on. On the vulnerability side of things, we created a estimation tool to directly estimate the seismic demand and capacity of infilled RC buildings. This tool integrates strength deformation relationships calibrated on a series of cloud analysis, carried out on a large data set of sampled equivalent single degree of freedom oscillators, and using average SA as the principal intensity measure. Now this tool requires low-level input, such as model analysis and SPO results, to estimate probabilistically the dynamic capacity of an MDOF system. And besides the fact that the tool is open access, perhaps its biggest advantage is that the dynamic capacity gets estimated more efficiently and in a probabilistic way, allowing the user to leverage on fundamental concepts in performance-based earthquake engineering, such as uncertainty propagation. And how does the application look like? Well, you essentially need to build a sufficiently detailed numerical model to account for all possible failure mechanisms, perform a model analysis, followed by a static pushover analysis to characterize the lateral response of the case study building as a function of the base shear and the global roof displacement. Then the user should multilinearize the SPO curve, indicating the onset and end of each response branch. And the tool will do the heavy lifting, meaning that the dynamic capacity of the system will get directly estimated using the integrated strength deformation relationships. The results from the response estimation tool are then integrated with different closed form expressions from different guidelines and existing literature to estimate the quantities related to the seismic demands and for each prescribed limit state along the height of the structure, namely peak story drifts, peak floor accelerations, and residual peak story drifts. For example, the deformation-based methodology of Muho et al. Was used to estimate the peak floor acceleration demands along the height of the case study structure, and this procedure incorporates the PGA levels at each limit states, which were previously mentioned in the hazard component. With regards to seismic risk, particularly the collapse risk, the mean annual frequency of collapse is a paramount component of PB loss and in the construction of the loss curve. To this end, we use the IM-based closed form solution proposed by Van Vatsikos in 2013 for the direct estimation of the collapse risk, or lambda C. And lambda C is a function of the resulting K0, K1, and K2 coefficients from the second order fit to the average SA hazard curve and the median collapse intensity and associated dispersion that are direct outputs from the response estimation tool. Then with regards to consequences, the building-specific direct economic losses are typically expressed as a function of the expected annual loss metric. And this metric is evaluated by integrating the vulnerability curves with the site hazard. That first expression, that first term, is the direct economic losses, which is the sum of three mutually exclusive, collectively exhaustive events conditioned on the ground motion intensity IM. 1, non-collapse requiring repair. 2, non-collapse requiring demolition. And 3, total replacement due to collapse. The first event is associated with repairs conditioned on the building not to be demolished nor to be expected to collapse. The probability of no demolition is estimated by simply entering the demand-based demolition probability curve constructed with a median of 1.5% of residual peak story drift and a dispersion of 0.3 as suggested by Ramirez and Miranda, and reading off the value on the y-axis corresponding to the intensity measure level at each limit state. The probability of no collapse is estimated from the collapse fragility curve that is constructed using the collapse median intensity and dispersion directly obtained from the response estimation tool. For repair costs, we leverage on the concept of story loss functions, which was introduced by Ramirez and Miranda back in 2012 as an excellent alternative to the computationally expensive FEMA P58 component-based approach, where the seismic demands and the expected repair costs are directly related using these functions, which can be directly estimated. To calculate the expected repair cost ratio, PB loss integrates generic SLFs that were derived for 4 different story or floor typologies and 3 non-structural component groups typically found in buildings that belong to the infilled RC typology. The event of demolition conditioned on non-collapse is governed by the residual drifts sustained by the structure, and these quantities are an indicator of potential dynamic instability, and buildings that suffer excessive residual drifts are irreparable and require demolition. And we've seen in the previous sections how we can estimate these curves, how we can construct these curves to estimate the required values in the determination of the overall losses associated with that kind of event. Now that last event is conditioned on the total replacement given the collapse of the structure, where the collapse fragility is constructed using the output of the response estimation tool and associating it with a suitable replacement cost that is generally found around the order of 1,200 euros per square meters. This procedure is repeated for all of the NTC 2018 prescribed limit states and 2 additional ones, namely the zero loss and collapse, until the loss curve is constructed, and the AL metric is evaluated integrating under the loss curve. Finally, we present the results of the end-to-end application of the proposed PB loss approach that is carried out on a set of 70 archetypes split between GLDs and SSDs. The results are compared to other scientific methods, such as DEAL, which was proposed by Cardone et al., and the existing Italian guidelines for risk classifications adopted in parallel with SISMA bonus. This is done in comparison with the outcomes of FEMA P58 component-based approach, which integrates the results of extensive nonlinear time history analysis in software called PAC, and we've considered these to be the benchmarks for our validations. While the existing methods seem to be internally consistent in their estimation of the expected annual loss metric, we can see that PB loss has consistently overperformed the other methods that are existing in the literature, which is more suitable for a better communication of seismic risk and economic losses. And we hope that through this validation, you have seen how PB loss is able to outperform all the other methods and perhaps could be an excellent alternative to be integrated with the SISMA bonus guidelines. And right now, I'm almost at the halfway mark of my presentation, but at the time, we were just kicking off the 4th year, and we knew that we weren't going to conclude there. And it wasn't until we presented the previous work at one of the Rose seminars that ideas from different participants came pouring in, including my good friend Petros Kalakonas and Professor Haluk Sujoglu, who we will probably have in the audience as keynote lecturer tomorrow, as they both suggested that we take advantage of all the numerical models that we've developed and the extensive validation runs to take things to a larger scheme and derive fragility functions for regional applications or typologies. One of the missing components was to define a suitable set of building classes and bin the developed numerical models accordingly. Now, this definition of a building class is a key step towards assessing seismic risk, and building classes must be defined using building attributes relevant to seismic vulnerability. To this end, we've selected the number of stories and design code levels as proxies for the vulnerability of these structures, and we've binned the numerical models as we've identified 4 prominent building classes: low code low rise, moderate code low rise, low code mid rise, and moderate code mid rise buildings. The only remaining decision here was the selection of our damage-based thresholds to reprocess the analysis results. And so we've adopted a hybrid definition for the damage states, taking advantage of the recent experimental campaigns conducted by Kurukala Surya et al. For the definition of serviceability limit states, since the response of the structure at these early points is governed by the damage to the masonry infills. Whereas the Italian code standards were used for the definition of the ultimate limit states, namely life safety and collapse prevention, integrating local response parameters such as the ultimate code rotation and different strength, local strength response parameters. Numerical collapse is achieved by exceeding a 5% maximum interstory drift. And the only thing remaining was to ensure prospectively, we had to also ensure prospectively that these quantitative damage definitions were consistent with how empirical data was characterized using the IDIS form. For the subsequent, of course, verification of the fragility functions. For those of you who are not familiar with the IDIS form, it is a printed rapid post-earthquake damage evaluation survey that is used by qualified inspectors since 1998 and to survey the structural damage of buildings after the event of an earthquake. To do so, we've assumed an objective-based relationship that we've deemed suitable for this sort of validation between the analytical and empirical fragility functions. The first product was a set of analytical fragility functions expressing the probability of exceeding the entire range of seismic response from serviceability to collapse and derived for the entire set of building classes, considering average spectral acceleration as the principal IM. Now, the second effort of this section was to derive empirical fragility functions for verification and validation purposes. And empirical fragility functions are the consequence of convolving 2 layers of information, namely the observed damage data and ground motion fields or shake. Currently, the common practice following shaking events, NGV or USGS shake maps, is to simulate ground motion fields for intensities that are compatible with the Uniform Building Code. This means PGA, spectral intensities at 0.3, 0.6, and 1 second However, to accommodate for the most recent findings in intensity measure efficiency, we've decided to go with average spectral acceleration as our principal IM for this study. For observed damage data, we relied on the DADO database, which is an IT platform maintained by the Italian Civil Protection Agency and the U-Center Foundation. The database contains data following 12 events, out of which we selected 2 as our case study events, which would be the Umbria Marche event of 1997 and the L'Aquila event of 2009. Information on building characteristics and spatial distributions of the inspected buildings is available and was gathered directly from the DADO database. This data contains information on the building's period of construction, number of stories, and damage states, which were crucial in the discretization and binning of the inspected buildings in a manner that is consistent with the predefined building classes for the analytical fragility function derivation. Now, simulating physically realistic ground motion fields, or GMFs, is a combination of, first, the ability to handle ground motion models for the estimation of spectral intensities, and for this, we went with the Bindi et al. Ground motion model, as it is the standard that is adopted by the INGV for the generation of shake maps. And we went with the indirect approach that was highlighted by Kohrangi et al. In 2018 to estimate SA average values and the total associated uncertainty. Another important component was the conditioning of these ground motion models on station data that was gathered from the Ithaca database to account for the ground truth in the within event uncertainty following the methodology proposed by Engler et al. In 2022 for the USGS shake maps. Spatial correlation was also considered to consider the spatial dependence in the joint probability distribution function of an intensity measure given a rupture scenario. Cross-correlation was also an important aspect of the development of these ground motion fields for the consistent sampling of ground shaking intensities from a ground motion distribution over multiple intensity measure types while still preserving the spectral shape properties. Luckily, fortunately, GEM maintains a comprehensive database of ground motion models and their variants and cross-correlation and spatial correlation models, which facilitated the derivation and the development of the work that was developed in this section. Then GMF simulations were carried out using a multivariate normal distribution, which is parametrized by a vector M of intensity measures given a rupture scenario I at site J, and a covariance matrix that incorporates the sources of between and within event uncertainties, accounting additionally for the spatial and cross-correlation components. First, the ground motion field for a simple PGA case was simulated to validate that the fundamental components of this procedure were consistent with the findings of official institutions such as the INGV. And after verifying that these ground motion fields match in terms of spatial distribution and amplitudes of the intensity measures, we can safely move on to the slightly more complex average SA case and simulate 2 ground motion fields associated with the SA average-based intensities that were conditioned on the taxonomy periods of 0.25 seconds for low-rise buildings and 0.50 seconds for mid-rise buildings, overlapping the ground motion fields with the data of observed damage, combining it with robust and conventional statistical methods for the derivation of fragility functions, leads to empirical fragility functions denoting the probability of exceeding distinct and expressed as a function of average SA. These functions were derived for all the identified building classes and considering the 2 case study events. By first comparing the dispersion values associated with the fitted empirical average SA fragilities to that obtained from conventional IM, such as the spectral acceleration and PGA, a significant reduction in the overall uncertainty for these considered building taxonomies can be observed, which highlights the notable benefit of considering average SA as the principal IM for regional applications. More so, a good match between analytical and empirical fragility functions was observed, considering the median intensities associated with the serviceability damage states, that is operational and damage limitations, with reasonable errors varying between 0 and 16% across all building classes for these initial damage states. However, for the ultimate damage states, it can be seen that the analytical fragility functions tended to consistently overestimate the median intensities with respect to the empirical observations. And unfortunately, but fortunately, No conclusions can be withdrawn with regards to collapse, which is consistent with the findings of other studies which have demonstrated that aspect. And these similarities and discrepancies between the analytical and fragility functions may be due to many sources, including the quality of data, particularly for the 1997 Umbria-Marchi sequence and the IDIS form before 2002, which was enabled to encompass all potential structural component types, leading to an equal classification of the seismic behavior among typologies that appeared similar aesthetically. Damage accumulation is an important component that contributes to these discrepancies, as data was collected following the conclusion of earthquake sequences to ensure the safety of the inspectors. And damage accumulation highlights the importance of considering other components in the analysis, in the analytical analysis, such as input energy, hysteretic energy dissipation, and proper ground motion record selections to characterize the response to main shock aftershock sequence. But perhaps more light will be shed on this matter during my colleague Nevena's presentation, so please hold on to your seats for that one. The uncertainty of the ground shaking prediction and site conditions can also influence the verification between analytical and empirical fragility functions, as of course the harmonization and damage state definitions between the Italian code and the macroseismic scales, which was a big assumption to begin with. And of course, last but not least, the bias in the data collection due to the difference in damage state perception, meaning the subjectivity from one evaluator to another. To wrap things up, we propose a simplified pushover-based procedure for the risk and loss-based assessment and classification of existing non-ductile infilled RC buildings. This procedure integrates state-of-the-art closed-form solutions, is probabilistic in nature, as some of its components consider uncertainty. It reduces significantly the computational demand when compared to the FEMA P58 comprehensive approach, while still offering acceptable and significant levels of accuracy and reliability. The procedure is reproducible to other building classes, of course, and is ready for integration with the current Italian guidelines for risk classification of existing buildings. To find out more about the key components and validations that went into the derivation of the PB loss procedure, the entire documentation has been peer-reviewed and is available for consultation as published works. On the regional application side of things, we've derived both analytical and empirical fragility functions using distinct subclasses of the infilled RC building class and, of course, the average spectral acceleration, our protagonist for this presentation, as the intensity measure. The analytical functions were derived using the compiled database of archetype numerical models and a hybrid damage state definition based on experimental findings and code-based prescriptions. The empirical functions were derived considering the DADO database for damage characterization and simulated average SA-based ground motion fields conditioned on station recordings. Extended versions of this talk are available on YouTube as part of 2 editions of the ROSE seminar. These videos provide more detailed insights and additional content that we couldn't cover here today, unfortunately, due to the time constraints. But if you have any questions or comments, please do not hesitate to reach out or connect with me. I'll be more than glad to chat with you about this or anything else, really. Thank you again once more for attending this presentation. I'll be more than glad to take your questions.
So thank you, Mo. And let's move on to the questions now of the evaluation panel. Xavier.
Thank you for this very interesting and comprehensive presentation. I mean, it was very nice. And I see that you synthesized the large portion of your thesis in very few slides, so you skipped a lot of things, which, I mean, you showed the overview, but still, I mean, you skipped a lot of interesting details. And probably, I mean, I have 2 questions that probably I'll go to those details. So my first question is, you mentioned at some point that you use cloud analysis, right? And I was wondering, so how many ground motions you are using in your procedure, in defining your procedure, or what you suggest, and how to select those ground motions?
Okay. Thank you very much for the comment. It was tough 4 weeks to condense 4 years of research into 25 minutes, but somebody had to do it. To correct a misconception, we did not actually do, are you talking about the cloud analysis of the proposed
methodology.
tool, of the tool, right? Yeah. Okay. So this cloud analysis takes into account 500 ground motion records that were selected for a suitable range of magnitude and distance ranges, and taking into account multiple intensity measure levels along the way so that we are able to characterize the structural response from early on from the elastic range all the way to structural single degree of freedom systems.
Okay. And the database, of course, is available in the GitHub. Yeah.
Yes.
So, and my second question is more related to, again, the methodology. So your methodology is mostly IM-based, right? Every step of the way is IM-based.
Sure.
But the loss curves that you are deriving, or the story loss curves that you are deriving based on that tool that you showed are EDP-based. So how did you do the conversion between EDP to IM just to get the final curves?
Thank you very much for your question. So we've explained along the way what were the approximation methods that we used to derive those EDP quantities, meaning the peak story drift, peak floor acceleration, and residual peak story drifts. So we've decided to integrate based on the strength deformation, the dynamic strength deformation relationships that we get from the tool, a series of approximations. First, for the estimation of peak story drift demands, for example, we can simply read off, as you can see, from the IMs at each code-based limit state, the corresponding ductility, and using a first mode approximation, we can relate that to the displacement at each story, and by then we can simply derive the drifts that are corresponding to each limit state. So that's one on the peak story drifts. For peak floor acceleration, we use a deformation-dependent approximation that uses these drift values at every story level to approximate using an empirical set of parameters the amplification factor, which is a function of the peak floor acceleration, and the PGA that is expected at each intensity measure level at each code-based limit state to estimate the peak floor acceleration demands. And to remain simplistic, we went with the FEMA P58 approach for the characterization of the residual peak story drifts, which we can simply get as a function of the yield drift of these structures.
Okay.
Thanks for the presentation of the methodology, very comprehensive work. I would like you to expand on the point related to the correspondence between AEDES damage and DS. If you can provide a tad more detail on the assumptions you made there.
Thank you very much for the question. I'll be happy to expand on that. So, the derivation of analytical fragility functions is a simple enough task because we've got the code-based limit states that quantitatively express the damage states as a function of local response or global response parameters. The challenge here in this study, which was observed probably by the similarities and the discrepancies, was how can we relate those to the empirical observations using the AEDES form. Now, we had to stick with it. We had to stick with our guns. So, using an objective relationship here to relate both NTC 2018 and the experimental findings with the empirical data seemed to have been suitable enough to capture the initial damage states, which were at serviceability, but weren't good or solid enough to carry us home, to take us home. So this hybrid approach, like on functionality, on safety and immediate occupancy, this was our way to go. Of course, we can integrate many refinements along the way until we're there in validating in analytical against empirical data, which remains still a challenge in the earthquake engineering community.
Do you think that the final overestimation you see in the end is related to this? To what extent the final overestimation, the behavior in terms of overestimation for significant damage and damage limitation, basically. How much is, what is the correlation?
As we pointed out, there are many different sources of these things. Obviously, the estimation, well, quantifying and relating empirical analytical can significantly influence whether our fragility functions are shifted left or right internally compared to each other. We believe that it does influence, particularly, like for example, collapse analytically was considered as 5%, which is a big margin, obviously, but we just wanted to be sure that, okay, if we reach 5%, our numerical model is not going to resurrect. It's collapse. But other components, such as damage accumulation, are even a significant component to this discrepancy, which was highlighted by the initial 2 damage states, because buildings that have not suffered damage limitations, if we compare analytical with empirical models, they should match more or less. It's not until we push the building enough into the nonlinear range of response that this damage accumulation component will be a considerable factor in how we relate empirical and analytical fragility functions. To answer your questions, I believe both factors play a solid role in this discrepancy.
Thank you.
Okay, congratulations. Very, very good study, and a lot of work have been done. So actually, you already answered to my question during your presentation, but just I wanted your opinion. You mentioned that you applied this methodology on 2 cases, 2 earthquakes, L'Aquila and
Umbria Marche.
And you saw some, you present some maps, over there. But I wanted your opinion that to which extent did you take all the characteristics of both earthquakes in order to have, let's say, good or bad results achievement and compare to the real damages that those earthquakes produce? And I will be more directly. So you mentioned that you take also shake maps or whatever, but there is some other issues regarding the response, particular site effects, ground condition, and also topographic effects, level of underground water table, and I can continue. So what do you think those effects can have some influence on the maps that you show of the damages of the buildings?
Thank you for your comment and for your question. Yes, for sure, site conditions, VS30, water table, whatever you want, yes, they influence greatly and significantly the generation of these ground motion fields. For the derivation of these ones, we used the microzonation study that was derived by Federico Mori et al. In 2021 that mapped the entire Italian peninsula in terms of VS30 values. To use those ones, obviously those values were using some sort of regression to map this entire, that component of VS30, and it can influence significantly the response of the ground motion model and its prediction on the estimated intensities. Now we try as much possible to constrain the ground motion models, whether with conditioning on station data, using appropriate spatial correlation models, etc. Unfortunately, there is no way to validate the average SA-based ground motion fields because it's let's say it's a pioneering study. But we were able to go on and validate the PGA values with regards to the INGV products. So that gave us a push towards that we're going in the right direction here. And let's just keep following our hunch on that one. But yes, to answer your question, if we have appropriate site conditions, by all means, it can influence significantly the results at the end.
There is time for 1 or 2 questions from the audience, if there's any. Okay, so I can ask a quick question. Okay. Flavia, go ahead. Go ahead, Flavia. No. You have the priority.
Just one. You mentioned that at the end that the methodology can be expanded to other structural typologies.
what would you see as the major barrier to expand to other structural typology? Do you think we have the same level of maturity of tools for other structural typologies?
That is a great comment. I do believe that PB laws can be integrated and can be expanded to other typologies because it's basically a set of independent components, but they work so well in harmony together to produce an estimation of the metric of our interest. For example, for the vulnerability estimation, it's simply recalibrating a set of SDOF oscillators to account for the hysteretic back of other building typologies. Another component that can be changed could be the story loss functions that we've adopted here, because different typologies come with different standard definitions of the acceleration sensitive components, drift sensitive components, etc. So that is also one other aspect that can be adopted. And I believe we've got solid tools along the way to help this effort go a long way. For example, story loss functions were derived based on an SLF generator toolkit that was derived by David Shahnazarian, who we have in the audience here, which is a solid tool, easy to use, open source toolkit that allows you to manipulate different typical damageable inventory, produce story loss functions in an easy manner. All we need is a bit of exposure in the scientific communities to all these tools. Of course, we don't have the time for everybody to be exposed to everything at the same time, but we should really give it a shot and be more familiar with these open access tools that will help us a long way, I believe.
Thank you.
Okay, so I think we are now all ready to get some coffee. So thank you very much, Moyet.
Thank you very much.
So we now have a half an hour break, so it's enough time for you to relax a little bit downstairs in the residence restaurant, and we'll see each other here to restart at 4:45.